Right now, as you're sitting here watching this video, the universe is doing something almost impossible to wrap your head around. Entire galaxies, each one holding billions of stars, are slipping away into a cosmic horizon we will never cross again. They don't move because they're flying away through space, but because space itself is stretching, carrying them further and further from us. Imagine a moment where something that once seemed eternal, the stars, the galaxies, the very night sky, quietly vanishes, not with a bang or explosion, but by simply drifting past the limits of what we can ever see. That's happening right now, in this very second. We've been told since childhood that space is empty, a giant nothingness that just sits there while planets and stars move around inside it. But that picture is completely wrong. Space isn't passive, it isn't still, it bends, it warps, it vibrates with invisible ripples, and perhaps the most shocking thing of all, it grows. To understand what that means, you have to let go of the idea that the universe is a giant room with walls or boundaries. Instead, think of it as a stage that keeps expanding while the actors stand still, a stage that never stops getting bigger no matter how much of it we try to map. This realization didn't come easy. For most of human history, we assumed the universe was calm, stable, even eternal. Then, in the blink of an eye, evidence appeared that shattered everything we thought we knew. What astronomers saw was so strange, so against intuition, that even Einstein himself dismissed it at first. But as the truth came into focus, it became clear we live in a universe not only vast, but restless, unpredictable, and maybe even destined for an ending more haunting than we can bear to imagine. For as long as humans have been looking up at the night sky, the darkness between the stars has carried a kind of quiet menace. It looks empty, silent, infinite. For centuries, that's exactly how people described it. An endless void, a backdrop where the real action happens. Stars are born, planets spin, comets streak across the heavens, and in between all of that, there is just nothing. Or at least that's what we thought. But here's the unsettling truth. Space is not empty at all. It only looks that way. If you could peel back the darkness, if you could zoom in far beyond what our eyes can detect, you'd discover that space is filled with hidden energy, invisible fields and structures so bizarre that they defy common sense. Think about it this way. If space really were nothing, absolute emptiness, then nothing could happen inside it. No waves, no expansion, no bending of light. But scientists noticed strange clues, little whispers that suggested the void itself had secrets. One of the first signs came when astronomers saw how starlight bent as it passed near massive objects. It wasn't the star doing the bending, it was space itself, curved under the weight of gravity, like a stretched sheet sagging under a heavy ball. This wasn't emptiness at all. It was a flexible, dynamic fabric, a stage that deforms and reshapes itself depending on what sits on it. Einstein predicted it with his theory of general relativity, but even he didn't fully imagine just how alive space could be. And that's only the beginning, because if space can bend, it can also ripple. In fact, in 2015, scientists finally detected gravitational waves, tiny vibrations in the fabric of reality, caused by two black holes colliding over 1 billion years ago. These waves traveled across the cosmos, through galaxies, through clusters of stars, across unimaginable distances, until they reached Earth. Our detectors, sensitive enough to notice a change smaller than the width of a proton, picked up that faint shiver, and in that moment it was confirmed. Space itself can move. It isn't static. It can be stretched, squeezed, and disturbed, like an ocean with invisible tides. But it gets even stranger. Between the galaxies, in what looks like nothingness, lies a sea of invisible particles and fields. Neutrinos, tiny ghost-like particles, stream through your body right now by the trillions every second, almost never interacting, as though you weren't even there. There are also quantum fields, unseen yet fundamental, humming everywhere in the universe. Even in a perfect vacuum, even in the most remote corner of intergalactic space where not a single atom floats, these fields fluctuate. Virtual particles pop in and out of existence, borrowing energy from nothing before disappearing again, like sparks flashing in a dark room. It's called quantum foam, and it suggests that empty space is anything but. It's restless. It's alive. This changes the way we think about reality itself. Imagine you're standing in a giant theatre, the lights go out, the stage looks black, and you assume it's bare. But if you walk out there, if you touch the floor, you'd realize the stage itself is alive, humming with hidden machinery under the surface, vibrating with unseen gears and currents. That's what space is. It's not a container, it's the machinery itself. Without it, nothing could exist. Because everything we see, galaxies, stars, planets, even us, depends on the properties of this invisible fabric. The most shocking part, though, is that space doesn't just sit there. It grows. When astronomers measured distant galaxies, they discovered something so counterintuitive, it almost felt like a cosmic prank. Those galaxies weren't just moving through space, they were being carried away because space itself was expanding, stretching like an inflating balloon. And here's the part that really warps the mind. There is no center to this expansion. Every point in the universe is moving away from every other point, not because galaxies are traveling outward, but because the very fabric in between them is increasing. It's as if you drew dots on a balloon and then blew it up. From the perspective of any one dot, all the others appear to drift farther away. But the truth is, the surface itself is what's expanding. That's our universe. Space itself is restless, always changing, dizzy in motion. And here's something even more unsettling. There may be more energy hidden in empty space than in all the stars combined. Physicists call it dark energy, a force so mysterious it seems to be accelerating the universe's expansion. Think about that. All the galaxies we can see, every burning star, every supernova, every black hole, all of it might make up only a tiny fraction of reality. The rest is invisible energy woven into the very structure of space. When you look up at the stars at night, the darkness in between is not an absence of light, it's a clue that the greatest force in the universe isn't what shines, but what hides. For a long time, people clung to the idea that the cosmos was eternal and unchanging. The stars might move, but the universe itself, stable, fixed, predictable. The idea of an expanding, dynamic fabric of space seemed too bizarre. Even Einstein, when his equations first hinted at it, thought he must have made a mistake. He introduced what he called the cosmological constant, a kind of mathematical patch, just to force the universe to look static again. Later, when Edwin Hubble observed that galaxies were indeed moving away, Einstein called that patch the biggest blunder of his life. But was it really a mistake? Or was it a glimpse of something deeper, this hidden energy that we now suspect is driving the expansion itself? All of this forces us to confront an uncomfortable truth. The universe is not built on solid ground. The foundation of everything is not matter, not atoms, not particles you can hold or see, but a shifting, invisible fabric that defies our instincts. And that fabric is not calm. It seethes with energy, bends under gravity, ripples with violent collisions, and stretches endlessly outward. It means that nothing is not nothing. Nothing is the stage on which everything plays out, and the stage itself is always rewriting the script. And once you accept that space is not empty, once you let go of the illusion of stillness, you start to see the universe differently. Every twinkle of a star, every swirl of a galaxy, every faint shimmer of light in the night sky is just part of a grander, restless whole. The blackness between the stars isn't silence. It's the roar of a universe expanding, humming with hidden forces we barely understand. And as shocking as that realization is, it's only the beginning. Because once scientists discovered that space itself was alive with hidden energy, the next question became even more unsettling. If the universe is expanding, then where is it heading? And what does that mean for us? If there's one idea that helps us wrap our heads around the expansion of the universe, it's the balloon analogy. At first glance, it seems almost childlike, too simple for something as vast and complicated as the cosmos. But don't underestimate it. This comparison gets right to the heart of why space expansion is so strange, and why it continues to puzzle even the greatest minds. Imagine a balloon, perfectly smooth and round, and now take a marker and draw little dots across its surface. Each dot represents a galaxy, fixed in its spot. Now start blowing air into the balloon. What happens? The balloon's surface expands, and as it does, every single dot moves away from every other dot. Not because the dots themselves are crawling across the balloon, but because the surface itself is stretching. From the point of view of any one dot, all the others seem to drift farther and farther away. That's exactly how the universe behaves on the grandest scale we can measure. But here's where the illusion gets tricky. You might be tempted to ask, okay, but where's the center of the balloon? Where's the middle of this expansion? The unsettling answer is that there isn't one. Not in the way we imagine. The balloon's surface doesn't expand into a particular point. Every part of it expands equally. The same is true for our universe. It isn't a bubble growing into some larger empty space. The fabric of reality itself is what's increasing. That's why no matter where you stand, it always looks like everything else is moving away. To us, here on Earth, it feels like we're at the center of the expansion. But someone billions of light years away, standing on their own planet, would see the exact same thing. Every point is the center, because the expansion doesn't need a middle, it happens everywhere at once. This idea is so hard to grasp, because our everyday experience doesn't prepare us for it. When things expand here on Earth, they expand into something. A balloon grows into the air around it. A drop of ink spreads into water. A fire burns into the oxygen nearby. There's always a container, always a space to grow into. But the universe flips this logic upside down. Space itself is the thing expanding, and it doesn't need anything to expand into. There is no outside. There is no giant empty room the universe is filling. Space is the room, and it just keeps stretching without limit. To really feel the weirdness of this, let's return to our balloon. If you're standing on one of those dots watching all the others move away, you might think you're special. You must be at the center. But if you could teleport to another dot, the view would be the same. Every galaxy feels like it's at the middle, but none of them actually are. That's what scientists mean when they say the universe is homogeneous and isotropic on large scales. Homogeneous means it looks roughly the same, no matter where you are. And isotropic means it looks the same in every direction. On small scales, of course, things vary. Some regions have galaxies, some are void, but zoom out far enough, and the grand pattern of the universe looks surprisingly uniform, like the surface of that balloon with evenly spaced dots drifting apart. The balloon analogy also helps us understand why distant galaxies don't just move away slowly, but accelerate. When you stretch the surface, the dots farther apart from each other separate more quickly. On a balloon, the distance between two dots on opposite sides grows much faster than the distance between two dots sitting close together. The same thing happens in the cosmos. Nearby galaxies might drift apart at a modest pace, but galaxies billions of light years away race away at astonishing speeds. In fact, some are moving away so fast, carried by the expansion of space, that no matter how powerful our technology becomes, their light will never reach us. They're receding beyond what we call the cosmic horizon, the ultimate boundary of what we can ever observe. Now, here's where the balloon analogy starts to break down, and where things get really mind-bending. A balloon has an inside and an outside. When you blow it up, it grows into the space around it. Our universe doesn't have that. We're not sitting inside some bigger structure watching the edges swell outward. There are no edges. The universe is everything. When it expands, it doesn't expand into anything else. It just becomes more of itself. This is probably the hardest part to accept, because our brains are wired to think spatially, to ask what's beyond that. But in cosmology, the word beyond loses its meaning. There is no beyond. The balloon surface is all there is, and we are trapped on it, forever moving with its stretch. The analogy also teaches us something else subtle but profound. If you shrink time backward, deflating the balloon instead of inflating it, all the dots move closer and closer until they merge into one. That's the Big Bang, not an explosion in space, but the entire fabric compressed into an unimaginably dense state. The balloon didn't burst into existence into an empty room. It was the room. The universe began not as a fireball in a void, but as space itself in its most compact form. That's why cosmologists say the Big Bang happened everywhere. Every galaxy, every planet, every atom we know was once part of that single dense moment. When we look out into space, we're not just seeing distance, we're seeing time itself stretching backward toward that origin. And yet the balloon is only a metaphor. Real space is not two-dimensional like the balloon's surface. It's three-dimensional, stretching in every direction we can imagine. The balloon helps us visualize the principle, but the reality is far stranger. Space doesn't need a center because it's not expanding into something else. It's expanding in itself everywhere at once. That's why cosmologists sometimes call it metric expansion. It's the very scale of distance that increases. The ruler we use to measure space grows longer, but because everything grows with it, we don't notice on small scales. Atoms, people, solar systems, Even galaxies stay bound together by their own force. It's only on the vast cosmic level that expansion reveals itself, tugging galaxies apart across the gulfs of intergalactic voids. One of the most haunting implications of this balloon-like expansion is what it means for the night sky. Right now, we can still see galaxies billions of light years away, their faint light just barely reaching us after traveling for eons. But as expansion continues, many of those galaxies will slip beyond the horizon, vanishing from our cosmic view forever. Future civilizations millions or billions of years from now may look up at the night sky and see only a handful of nearby galaxies. The wider universe, the vast cosmic web we marvel at today, will have disappeared into darkness. Unreachable and unknowable, their balloon will still be expanding, but the dots on it will be too far apart to see one another. They may never even realize there was once a larger cosmos out there. And this raises a chilling question. Are we living at a privileged time in cosmic history? A moment when the universe is still young enough, still transparent enough, that we can witness the grand structure before it fades away. If that's true, then the knowledge we have today, the images of galaxies stretching to the edge of the observable universe, may someday be impossible to rediscover. The balloon will keep inflating, but the evidence of its beginnings will slip through our fingers. So the balloon analogy isn't just a clever way to explain expansion. It's a warning too. It shows us that the universe is dynamic, that what we see today is temporary, and that the very act of expansion hides its own past. Every second, the cosmos stretches wider, and while we can use physics and imagination to reconstruct its story, the view itself is disappearing. Just as a balloon gets thinner and harder to see as it inflates, the universe is making its own history harder to detect. We are racing against time, not the ticking of a clock, but the stretching of the fabric beneath our feet. And yet, this realization doesn't make the universe feel smaller or emptier. It makes it feel alive. The expansion is not just a backdrop, it's a character in the story of existence, a restless, unstoppable force that carries galaxies, light, and even the limits of human knowledge along with it. To understand it is to stand on one of those dots on the balloon and realize you are part of the grand motion, carried forward not by your own will, but by the ceaseless breath of the cosmos. And what that means for the future where this balloon is heading is a question that has shaken science to its core. By the early 20th century, most scientists believed the universe was calm, eternal, and unchanging. The stars glittered overhead like lanterns pinned to a vast ceiling, and many thought they had always been there, and always would be. The idea of a restless, growing cosmos was almost unthinkable. Even Albert Einstein, when he developed his revolutionary theory of general relativity in 1915, found that his own equations suggested something unsettling. The universe should be either expanding or contracting, but not sitting still. He didn't like that answer. It was too radical, too far removed from the picture most people had of a stable universe. So, to fix the math, he introduced what he called the cosmological constant, a kind of anti-gravity fudge factor that forced his universe to remain static. Later, he would look back on that decision and call it the greatest blunder of his career. But in truth, the real shock was still to come, and it would be delivered by an unlikely astronomer named Edwin Hubble. In the 1920s, Hubble was working at the Mount Wilson Observatory in California, home to the Hooker telescope, the largest in the world at the time. With that massive eye on the sky, he began cataloguing what were then called nebula, fuzzy patches of light scattered between the stars. Many astronomers believed these glowing smudges were just clouds of gas inside our own galaxy, small curiosities within the Milky Way's boundaries. But Hubble suspected something else. Using careful measurements and the newly developed techniques of analyzing the brightness of certain stars, he proved that some of these nebula were not part of our galaxy at all. They were galaxies in their own right, vast islands of stars, millions of light years away. The universe, it turned out, was far larger than anyone had dared to imagine. But that was only the beginning of his discovery. Hubble didn't just measure distances, he looked at the light from these galaxies. When he analyzed their spectra, he noticed something strange. The light was redshifted. That means the wavelengths were stretched toward the red end of the spectrum, the same way the pitch of a siren drops as an ambulance drives past you. This Doppler effect told Hubble that the galaxies weren't standing still, they were moving, and not just a little bit, they were rushing away from us, at tremendous speeds. At first, the idea seemed absurd. Why would every galaxy be running away from the Milky Way? Were we at the center of the universe, scaring everything else off? But as Hubble plotted more and more data, a a startling pattern emerged. The farther away a galaxy was, the faster it receded. It wasn't random, it was law-like, precise. This became known as Hubble's law, and it revealed the true nature of cosmic expansion. Galaxies weren't fleeing through space like bullets from a gun, they were being carried apart by the expansion of space itself. The balloon analogy we use today was born from this very realization. The shockwaves of Hubble's discovery rippled across science. The universe was not static, it was dynamic, stretching, evolving, and if it was expanding now, then logically in the past it must have been smaller, denser, hotter. Suddenly the door was open to the idea of a beginning, a cosmic birth that would later be called the Big Bang. Imagine the mindset of those scientists at the time, many of whom had grown up believing in a steady, eternal universe. Overnight, their worldview shattered. The cosmos was no longer a quiet stage where stars simply burned and faded. It was a restless, living thing, growing larger by the second. The resistance to this idea was strong at first. Even Einstein himself, upon visiting Hubble at Mount Wilson and seeing the data, was forced to admit he had been wrong. His blunder, the cosmological constant, wasn't needed to keep the universe stable. It was the opposite. The universe didn't want to be stable. It wanted to expand. Hubble's work forced scientists to confront a truth that was both exhilarating and terrifying. The night sky was not fixed, but in motion, every galaxy on a slow but unstoppable journey away from every other. Hubble's discovery also sparked one of the greatest philosophical debates in science. If the universe was expanding, what did that mean about its origin? Did it have a beginning? If so, what came before it? Many scientists, uncomfortable with the notion of a creation event, pushed back. They preferred models where the universe was eternal, with no beginning and no end. One such idea was the steady-state theory, which suggested that as galaxies drifted apart, new matter popped into existence to fill the gaps, keeping the density of the universe constant. But decade by decade, evidence piled up against this view. The redshifts Hubble measured were undeniable. The galaxies were moving apart, and the universe was not steady at all. To grasp the true weight of Hubble's discovery, imagine living in that moment in history. For centuries, humanity had struggled to understand its place in the cosmos. First, Earth was the center of everything. Then, it was just another planet orbiting the Sun. Then, the Sun was revealed to be just another star in a galaxy of billions. And now, thanks to Hubble, even the Milky Way was just one of countless galaxies, all receding into the darkness. Each step made us smaller, less central, less special. But it also made the universe grander, stranger, more awe-inspiring. The stage of existence wasn't just vast, it was expanding as though reality itself were breathing in slow motion. And yet the story of Hubble's shocking discovery doesn't end with that first realization. It set the stage for deeper mysteries. If the universe was expanding, then what was driving it? What hidden force pushed galaxies apart? And if it had a beginning, what was its fate? Would it expand forever, growing colder and darker, or would gravity someday pull it back together in a fiery collapse? These questions turned Hubble's data into a cosmic riddle, one that scientists are still unraveling today. Looking back, it's astonishing to think how fragile the evidence was at first. Smudges of light on photographic plates, painstakingly measured by hand, tiny shifts in spectral lines that hinted at unimaginable truths. And yet, from those faint marks, Hubble unlocked a secret bigger than anything science had revealed before. The universe itself was alive with motion. The galaxies were not just distant lights, they were travelers, carried along by the restless expansion of space. The most chilling part of all is that Hubble's discovery implied something that feels almost impossible to accept. The night sky is temporary. The constellations we know, the galaxies we glimpse through telescopes, the vast cosmic web we map across billions of light years, none of it is permanent. Given enough time, the expansion will erase our view. The galaxies will drift beyond sight, their light stretched into invisibility. Future observers, trapped in their own tiny island galaxies, may never know the truth. They may believe the universe is small and static, just as people once did before Hubble. We here and now are lucky, or perhaps unlucky, to live at the brief moment when the evidence is still visible. So, when we talk about Hubble's shocking discovery, it's not just a story of one man with a telescope. It's the story of a turning point in human understanding, the moment when the universe stopped being eternal and started being alive. It's the moment when we realized we are passengers, not on a still stage, but on a balloon inflating without end. And what lies at the end of that expansion, whether it's silence, collapse, or something stranger than either, is a mystery that began with Hubble's first redshifted galaxies. When Edwin Hubble first noticed that the light from distant galaxies was stretched toward the red end of the spectrum, it looked like a technical detail, something only specialists would care about. To the average person, a galaxy was just a smudge of light in the telescope. To Hubble, that smudge carried within it a coded message, written in color. And once he cracked that code, the universe itself began to whisper its secrets. This was the redshift mystery, and it changed everything we thought we knew about reality. To understand why it was so shocking, you first have to know what redshift really is. Imagine an ambulance racing past you. As it approaches, the siren's pitch is high, but as it speeds away, the sound stretches, dropping into a lower pitch. That's the Doppler effect. Light behaves the same way. When a source of light moves toward us, its waves are compressed, shifting toward the blue end of the spectrum. When it moves away, those waves stretch, sliding toward the red. By measuring that shift, astronomers can tell whether something is approaching or receding, and how far. It's a simple concept, but applied to galaxies millions of light years away, it became a cosmic revelation. Hubble and his colleagues expected a mix, some galaxies drifting toward us, some away. After all, in a static universe, there should be no reason for motion to be one-sided. But what they found was far stranger. Virtually every galaxy outside our immediate neighborhood showed redshift, and the farther away the galaxy, the greater the shift. That meant not only were they all moving away, but the speed of their retreat increased with distance. It was as if the universe itself was stretching apart, dragging the galaxies along with it. At first, some scientists resisted this idea. Maybe the redshift wasn't motion at all. Could it be that light simply lost energy on its journey, fading into red with distance? This tired light hypothesis lingered for a while, offering a way to preserve the dream of a static cosmos. But experiments and observations soon crushed it. Light traveling across billions of years does not lose energy in such a way. The patterns of galaxies, the distribution of cosmic structures, the very fabric of space-time itself pointed to one conclusion: the redshift was real, and it meant expansion. Think about how radical that was. For centuries, philosophers and scientists had clung to the idea of an eternal universe. The stars might be born and die, but the cosmos as a whole was thought to be timeless. Now a simple shift in color suggested that wasn't true. If everything was moving apart today, then in the past, everything must have been closer together. Trace it back far enough, and the entire universe collapses into a single, unimaginably dense state. That implied a beginning, a moment when the universe itself came into being. It was such a disruptive idea that many scientists bristled at it, some even mocking it. The term Big Bang was originally coined as a joke by a skeptic of the theory, and yet the evidence mounted, and the redshift mystery refused to go away. The deeper scientists looked, the stranger it became. Redshift wasn't just about motion, it was about the very nature of space. Galaxies weren't racing through space like cars on a highway. They were mostly staying put, held together by gravity. What was changing was the distance between them, because space itself was expanding. Imagine ants standing still on a stretching rubber band. They don't move, but the space between them grows larger as the band is pulled. That's why the farther a galaxy is, the faster it appears to recede. More space is stretching between us and it, so its redshift is greater. This realization raised unsettling questions. If space was expanding, what was it expanding into? The answer, as strange as it sounds, is nothing. Expansion doesn't need a container. Space itself is the stage, and the stage is growing. That's why every observer, no matter where they are, sees the same thing: galaxies rushing away in all directions. There is no center. There is no privileged place. The redshift mystery revealed not just expansion but the dethronement of humanity from any cosmic middle. We are passengers in a universe that grows everywhere at once. But the mystery didn't stop there. As measurements became more precise, scientists noticed irregularities, tiny deviations from the neat pattern of Hubble's law. Some galaxies moved slightly faster, some slower, their motions influenced by local gravity. Others hinted at deeper complexities. Over time, it became clear that redshift wasn't just a clue about expansion. It was a map of the hidden forces shaping the cosmos. Clusters of galaxies tugged on each other. Dark matter, invisible but massive, warped the motions, and layered beneath it all was something even more sinister. The realization that the expansion itself wasn't steady. It was speeding up. That acceleration, discovered decades later, would be attributed to dark energy, a mysterious force making up nearly 70% of the universe. But the seed of that revelation was planted in Hubble's redshifts. Without them, we would never have realized that the cosmos is not only expanding, but accelerating into a future we can barely comprehend. What makes the redshift mystery so haunting is how invisible it is to the naked eye. Look up at the night sky, and nothing seems to move. The stars appear fixed, the galaxies like frozen smears of light. But hidden in their glow is the story of motion on the grandest possible scale. Each photon of light has stretched across the expanding fabric of space, carrying with it the signature of retreat. To detect it requires patience, precision, and a willingness to believe what your eyes can't see, that everything is rushing apart in slow, silent motion. It's almost poetic that light, the very thing that lets us see, is also the messenger of this secret. Every shift toward red is a cosmic postcard sent billions of years ago, telling us not only where a galaxy was, but where it's going. By reading those postcards, astronomers piece together the story of the universe itself. And like all great mysteries, the answer only led to bigger questions. If the redshift meant expansion, then what was the origin point? What powered the initial burst? What lies beyond the horizon we can no longer see? And perhaps most unsettling of all, if everything is stretching away, what will happen in the end? Will galaxies continue to drift until the night sky grows cold and empty, a cosmic graveyard of lonely stars? Or will some deeper force hidden within the redshift reveal a twist no one expects? The redshift mystery is a reminder that the universe doesn't always shout its secrets. Sometimes it whispers them in faint colors, subtle shifts that only reveal their meaning when we look closely enough. It took patience, daring, and a willingness to abandon old ideas for Hubble and others to see it. And once they did, humanity's vision of the cosmos changed forever. The sky was no longer static. It was alive, restless, moving, and each time we gaze at the faint red glow of a galaxy billions of light years away, we're seeing proof of that motion, evidence that the universe itself refuses to stand still. The deeper astronomers dug into the mystery of redshift and expansion, the more one conclusion seemed unavoidable. If the universe is stretching outward today, then long ago it must have been smaller, denser, hotter. Roll the clock back far enough, and everything we see, every star, every planet, every galaxy, was once packed together in a single, unimaginable moment. This idea, shocking in its simplicity, became known as the Big Bang. But here's the twist. It wasn't the kind of bang people imagine. It wasn't a fireball exploding into empty space, throwing galaxies outward like shrapnel from a bomb. No, the Big Bang was something stranger, deeper, and far more unsettling. It wasn't an explosion in space. It was an explosion of space itself. For decades, this distinction confused not only the public, but scientists too. When you hear bang, you picture a noise, a blast, something with a center that expands outward into an environment around it. But the universe had no environment, no outside to expand into. The Big Bang happened everywhere, all at once, because space itself was born in that moment. It wasn't that galaxies were scattered across a void. They emerged from the very fabric of the cosmos as it inflated. Every point we see today, from the Milky Way to the faintest galaxy at the edge of our telescopes, traces its origin back to that first instant. Every atom, every particle, every beam of light was forged in that incomprehensible beginning. This twist, that the Big Bang wasn't an explosion of matter into emptiness, but the birth of the very stage itself, is what makes it so difficult to picture. Our minds are used to containers, to rooms that things happen inside. But in this case, the room itself is the event. Before the Big Bang, there was no before in the way we understand it. Time itself was part of the explosion. Asking what happened before the Big Bang is like asking what's north of the North Pole. The question dissolves as soon as you realize the framework you're using doesn't apply. The term Big Bang itself came not from its supporters, but from one of its critics. In the late 1940s, Astronomer Fred Hoyle, who championed a rival theory called the steady-state model, mocked the idea during a radio broadcast. He called it the Big Bang as a way of poking fun, suggesting it was too crude, too cartoonish to be taken seriously. Ironically, the name stuck, and what began as an insult became the label for the most widely accepted cosmological theory of our time. Hoyle's steady-state model, which suggested the universe had always existed in essentially the same state, eventually collapsed under the weight of mounting evidence. But his sarcastic phrase survived, even if it misleads by making people think of the event as a blast instead of a birth. What really happened in that first instant remains one of science's greatest mysteries. The equations of general relativity, when pushed back far enough, break down at what's called a singularity, a point of infinite density where the known laws of physics no longer apply. That singularity is where the Big Bang story begins, but it's also where our understanding ends. Physicists have tried to pierce that veil with quantum theories of gravity, string theory, loop quantum cosmology, and countless other frameworks, but so far the truth remains hidden. Was the Big Bang the true beginning, or just a transition from a state we can't yet comprehend? Did the universe emerge from nothing, or from something stranger than nothing, a seething quantum foam that flickered into existence? These questions hover like shadows at the edge of our knowledge. What we do know is that in its earliest fractions of a second, the universe was unimaginably dense and hot, filled with a glowing soup of particles colliding and annihilating each other. Temperatures soared so high that atoms couldn't form. Even protons and neutrons were still coming together from a sea of quarks and gluons. In less than a heartbeat, the universe was already expanding at breakneck speed, and the energy of that expansion was creating the very ingredients of matter itself. This was no ordinary explosion. It was creation in its rawest form, reality assembling itself out of chaos. As the seconds ticked by, the universe cooled enough for atomic nuclei to form: hydrogen, helium, a sprinkle of lithium. These were the primordial elements, forged not in the hearts of stars, but in the very birth of time and space. For hundreds of thousands of years, the cosmos remained a glowing plasma, opaque to light. Then, as it cooled further, atoms formed, and the universe became transparent for the first time. The photons released in that moment still exist today, stretched by billions of years of expansion into a faint afterglow called the cosmic microwave background. It is quite literally the oldest light in the universe, a baby picture of creation, and one of the strongest proofs of the Big Bang model. But here's another twist. The Big Bang was not only about beginnings, it was about endings too. If the universe truly had a starting point, then it might also have a fate, a final chapter written into its expansion. That realization unsettled scientists as much as the discovery of the beginning itself. If everything started with a bang, would it end with a crunch? Would gravity someday halt the expansion, pulling all galaxies back together into a fiery collapse? Or would expansion continue forever, thinning the cosmos, until stars burned out and silence reigned? The Big Bang wasn't just a story of origin, it was a question mark about destiny. It's easy to forget how radical this idea was at first. For millennia, people believed the universe was eternal, unchanging, a backdrop that existed independently of time. To suddenly suggest that it had a birthday, that it was younger than the oldest stars, that it came into being in a single moment, this was a philosophical shock as much as a scientific one. It forced humanity to confront a cosmos that was not fixed, but dynamic, not eternal, but fleeting in its own vast timescale. It redefined our place, not as inhabitants of a permanent home, but as temporary passengers in a universe with a beginning, and perhaps an end. And yet, the Big Bang twist didn't close the book on mystery. It opened it wider, because if the universe could spring from a single instant, then what lies beyond our universe? Could there be others? Is the Big Bang just one of many bangs, one bubble in an endless froth of universe? Modern theories of inflation and the multiverse suggest this might be true, that what we call the beginning was just one event in a chain, or even an infinite sea of beginnings. If so, our universe may not be the story, but just one chapter in a book too vast for us to ever read. What's certain is that the Big Bang was no ordinary explosion. It wasn't loud, it wasn't fiery, and it didn't scatter galaxies into a void. It was the birth of space and time themselves, the stretching of a fabric that had never existed before. Every step you take, every breath you draw, every star you see at night, All of it is part of that unfolding, part of that ancient expansion that began in an instant too brief to imagine. And the fact that we can even glimpse this story billions of years later by measuring faint shifts in light and echoes of ancient radiation is a reminder of how extraordinary it is that we exist at all. The twist of the Big Bang is not just that the universe had a beginning, but that the beginning is still with us. The expansion hasn't stopped. The afterglow still surrounds us. The galaxies are still rushing away. We are still inside the event, carried outward by its momentum. The Big Bang isn't just history. It's happening right now, and what that means for our future is a mystery that only grows deeper the more we learn. If you've ever wondered what the universe looked like when it was a baby, the answer isn't hidden in imagination. It's written across the sky in faint, ancient light. This is the cosmic microwave background, or CMB, and it is the closest thing we have to a photograph of the newborn cosmos. It's not just a relic, not just a glow, it's a time machine, a snapshot frozen in radiation that carries us back almost 14 billion years, to a time when the universe was only a few 100,000 years old. To look at it is to stare into the cradle of existence itself. But to understand why the CMB is so important, you first have to rewind the clock. In the seconds and minutes after the Big Bang, the universe was a furious storm of energy. Temperatures were so high that atoms couldn't even form. Particles smashed into each other in a soup of plasma. Electrons and protons were constantly colliding with photons, particles of light, so tightly coupled that the universe was opaque, like the inside of a glowing star. Light couldn't travel freely. Every time a photon tried to move, it was immediately scattered by another charged particle. For hundreds of thousands of years, the cosmos remained a blinding fog of radiation and matter, dense and hot beyond imagination. Then, after about 380,000 years, something dramatic happened. The universe had expanded and cooled, just enough for electrons to settle down and bind with protons, forming the first stable atoms of hydrogen and helium. With electrons locked into orbits, the constant scattering stopped. Suddenly the fog lifted. Photons could travel freely for the first time, streaming across space without being constantly interrupted. That moment is called recombination, though in reality it was the first combination of matter and light into distinct forms. The glow released then is still with us today, stretched into microwaves by billions of years of expansion. That glow is the CMB, the baby picture of the universe. The discovery of this ancient light was itself a story of chance and mystery. In 1965, two engineers, Arno Penzias and Robert Wilson, were working at the Bell Labs Holmdel Horn antenna in New Jersey. They were trying to eliminate noise from their radio experiments, but no matter what they did, a persistent hiss remained. They even cleaned out pigeon droppings from the antenna, suspecting the birds were interfering. But the noise didn't go away. What they were hearing was not pigeons or equipment malfunction. It was the echo of the Big Bang itself, faint microwaves arriving from every direction in the sky. They had stumbled upon the CMB without even looking for it, and their discovery earned them the Nobel Prize. At first, the CMB seemed astonishingly uniform, the same in every direction, as though the universe had been smeared perfectly smooth. This uniformity was puzzling. How could regions of the universe so far apart, regions that had never had time to communicate with each other, all share the exact same temperature? This was the horizon problem, the same mystery that inflation would later solve. But when scientists looked closer, they found something even more remarkable. Tiny fluctuations in the CMB, subtle variations in temperature measured in millionths of a degree. Those faint ripples were the seeds of everything we see today, the tiny differences that gravity would later amplify into galaxies, stars, and planets. Without those ripples, the universe would have remained smooth, featureless, and lifeless. Over the decades, technology advanced enough to map the CMB with incredible precision. In 1992, NASA's COBE satellite first revealed those faint fluctuations. Later, missions like WMAP and the European Space Agency's Planck satellite refined the map, producing the most detailed portrait of the infant universe ever created. The Planck map showed the CMB with such clarity that scientists could measure the exact age of the universe, its rate of expansion, and even the proportions of its ingredients. About 5% ordinary matter, 27. The baby picture of the cosmos wasn't just beautiful, it was a scientific gold mine. The CMB also provided the clearest evidence yet for the Big Bang. Competing theories like the steady-state model could not explain why the entire sky glowed with the same faint microwave radiation. Only a hot, dense beginning could produce such a relic, and the detailed fluctuations matched the predictions of inflation perfectly, showing the faint fingerprints of quantum fluctuations stretched to cosmic scales. The discovery turned the Big Bang from a bold idea into an established cornerstone of cosmology. But the CMB is more than a proof of the past. It is also a window into mystery. Those tiny fluctuations, those faint patterns, are not random. They carry within them hints of deeper physics, subtle anomalies that some scientists think could point to new laws of nature. For example, some regions of the CMB appear slightly colder or hotter than expected, patterns that don't quite fit the neat predictions of theory. Is it noise? Or is it a clue to something bigger? Perhaps evidence of other universes brushing against ours, or physics beyond the standard model. The debate continues, but what's clear is that the CMB is not just history, it's a puzzle still unfolding. To grasp how profound this is, consider this. When you look at the CMB, you are seeing light that has travelled for almost 14 billion years, without interruption. It is the oldest light we will ever see, because before recombination, the universe was opaque. No telescope, no matter how advanced, will ever peer further back in light. The CMB is the wall, the cosmic horizon of vision. Beyond it lies the true beginning, hidden forever from our direct sight. And yet, even from that wall, we have extracted more knowledge than from any other observation in history. What's haunting about the CMB is how ordinary it looks at first glance. If you could see it with your eyes, it would be a faint glow, just a few degrees above absolute zero, invisible without special instruments. It doesn't dazzle like galaxies or shimmer like stars. It's a whisper, not a shout. But within that whisper lies the entire blueprint of the universe. It is the canvas on which time, matter, and life itself would later be painted. And it reminds us of something humbling. The universe keeps records. It carries with it the marks of its birth, the scars of its growth, the fingerprints of its expansion. The CMB is one of those records, a fossilized echo that connects us to the very beginning. Every time scientists refine their measurements, they are, in a sense, peering deeper into the baby's face, trying to see which features belong to nature, which to chance, and which to mystery still unsolved. We live in a time when that face is still visible. Billions of years from now, as the universe continues to expand and dark energy drives galaxies apart, the CMB will fade, stretched into wavelengths too long to detect. Future civilizations, if they exist, may never even know it was there. They may never guess that the universe had a beginning, or that faint microwave whispers once told the story of its childhood. We are privileged, in this cosmic moment, to see what they never will, the baby picture of everything. The CMB is more than data. It is a reminder that the cosmos, vast and ancient, still carries traces of its infancy, like a scar, a memory, a lullaby whispered across eternity. And when you realize that every star, every planet, every person exists because of the tiny ripples hidden in that ancient light, the truth becomes inescapable. We are not just living in the universe, we are living inside its story, and that story begins with the glow of a baby picture still written in the sky. One of the hardest things to grasp about the expansion of the universe is that it doesn't feel real. Look out your window tonight, and the stars don't appear to be drifting apart. The Milky Way doesn't stretch like a balloon, and the planets in our solar system orbit calmly as if nothing in the background is changing. Yet on the grander scales, space is swelling, galaxies are pulling away, and reality itself is widening like dough in an oven. To make sense of this, astronomers use an analogy that seems almost too simple but captures the essence perfectly. Raisin bread. Imagine dough filled with raisins placed in an oven. As the dough rises, each raisin moves away from the other, not because the raisins themselves are crawling outward, but because the dough between them is swelling. The farther apart the raisins are, the faster they seem to separate. That is the raisin bread reality, and it is one of the best ways to understand how our universe expands. The beauty of this analogy is how it explains the most counterintuitive part of cosmic expansion. That galaxies are not flying through space at breakneck speeds, but are carried along because space itself is stretching. From our perspective on Earth, it looks as though every distant galaxy is racing away. From the perspective of someone living in a galaxy billions of light years away, we would appear to be racing away from them. Both views are equally true. Just like each raisin in the bread, Every galaxy sees itself surrounded by others all receding, not because of motion through space, but because of the growth of space. This model also helps us understand why nearby galaxies don't appear to be drifting away dramatically. Raisins sitting close together only separate a little as the dough rises, while raisins farther apart are carried away more quickly. That's why galaxies within our local group, like Andromeda, don't obey Hubble's law in the same way. Gravity binds them tightly enough to resist the general swelling of space. But galaxies farther out beyond the tug of our local cluster obey the expansion fully, receding faster and faster the more distant they are. It's not because they are blasting away through the void, it's because the cosmic dough between us and them keeps stretching. And here's where the analogy becomes chilling. The expansion of raisin bread has no edge. From the perspective of any raisin, it looks as though it sits in the middle, with all others drifting outward. But in truth, there is no center. The dough doesn't expand into a larger space. It simply grows everywhere at once. That's why our universe has no middle. Wherever you are, it looks like everything else is moving away. Every observer is the center of their own cosmic raisin bread, and yet there is no true center at all. This is one of the most difficult concepts for the human brain to grasp, because in our daily lives, expansion always has a direction, always a container. But on cosmic scales, the container is the thing expanding, and it has no outside. The raisin bread analogy also illustrates why galaxies can appear to move away from us faster than light. If the dough is rising quickly enough, two raisins separated by a great distance can be carried apart faster than the speed of light, without either raisin actually moving faster than light relative to the dough. This doesn't violate Einstein's speed limit because the galaxies aren't traveling through space. They're being pulled apart by the expansion of space, and it's why some galaxies, though they emitted their light billions of years ago, will never send us another photon again. They are already receding beyond our cosmic horizon, carried away by the stretching dough faster than light itself can cross the gap. What makes the raisin bread reality even more profound is how it explains our cosmic isolation. Right now, we can still see the faint light of galaxies billions of light years away, their photons stretched red by expansion but still reaching us. But in the far future, as the dough keeps rising, more and more raisins will slip beyond our horizon. Their light will never reach us again, and the universe will grow darker, lonelier, emptier. Someday distant civilizations might look up at the night sky and see only their local cluster of galaxies, never guessing that the wider universe once revealed itself. The evidence of the grand expansion will be erased by the expansion itself. In a sense, we are living in a privileged time, one of the few moments in cosmic history when the universe still shows its hand. The raisin bread model also underscores something humbling. On large scales, everything is temporary. The galaxies we map, the constellations we trace, the great filaments of the cosmic web, all of it is fleeting. As the dough rises, these patterns shift, stretch, and eventually fade beyond reach. What feels eternal to us is just a snapshot in an evolving reality. Every dot in the bread is not fixed, but part of an unstoppable drift into isolation. And yet, not everything is swept away. Raisins that sit close together remain clustered, held by their own stickiness. In the universe, gravity plays this role. That's why our solar system is stable, why the Milky Way remains bound, why Andromeda is on a collision course with us instead of drifting away. On small scales, local forces overpower the expansion, but beyond those scales, the swelling dough dominates, carrying galaxies and clusters apart no matter how strong their pull might have once been. This is why we see cosmic structure on multiple levels. Stars bound into galaxies, galaxies bound into clusters, clusters woven into filaments, but all of it ultimately carried apart by the rising dough of space itself. This model also highlights the eerie inevitability of cosmic isolation. The galaxies nearest to us will remain in sight, gravitationally bound companions in a sea of darkness. But the others, the vast majority of the universe, will fade. Their light will stretch so far into the red that it becomes undetectable, lost in the blackness. The universe will seem to shrink, not because it actually contracts, but because our view collapses into loneliness. The cosmic bread will keep rising, but from our perspective, the raisins will vanish one by one into nothingness. The raisin bread reality is not just an analogy, it's a revelation about how strange the universe really is. We live inside a process that doesn't feel real, because on human scales, expansion is imperceptible. A loaf of bread doubling in size is obvious, But space doubling across billions of light years is invisible to the naked eye. Only by measuring redshifts, only by tracking the faint glow of galaxies do we see it. And once we do, the truth becomes unavoidable. The universe is not still. It is restless, swelling, rewriting itself every second. This analogy also forces us to face the question of destiny. If the bread keeps rising, will it ever stop? Will the dough collapse under its own weight, pulling the raisins back together in a cosmic crunch? Or will the expansion continue forever, leaving each raisin in solitude, the oven growing colder and emptier until there is nothing left but darkness? The raisin bread reality doesn't answer the question. It only makes clear that whatever the fate, it will not be static. The universe is not a loaf left on a shelf. It is one rising endlessly, its ingredients changing shape, its patterns shifting, its future uncertain. And the most haunting part of all is this: we are not outside observers watching the loaf in an oven. We are inside it. We are raisins carried along, passengers of the rising dough, unable to step outside to see the loaf as a whole. Our only clues are the light from other raisins and the stretch of space between them. From those clues, we piece together the truth, but the bigger picture will always remain beyond us. The raisin bread reality is both simple and profound, a model that makes the unthinkable just barely thinkable. And yet, no analogy can capture the full strangeness of the fact that reality itself expands. The universe is not a stage set once and for all. It is dough rising, a process unfolding, a reality that refuses to remain still. And every moment we live, every star we see, every galaxy we map is just part of that rising, part of the slow but unstoppable stretching that defines the cosmos. It is a truth as ordinary as bread, and as extraordinary as infinity. If you've ever stood at the edge of an ocean and watched the water stretch endlessly toward the horizon, you know the feeling of seeing something vast but knowing there's a limit to your view. No matter how far you look, there's a line you cannot see beyond, a boundary where the earth curves away and hides what lies further. The universe has its own version of this, a cosmic horizon, a boundary not of geography but of time and space itself. It's not a wall you could ever touch or cross, but a limit written into the fabric of reality. And what it reveals is both haunting and humbling. There are galaxies slipping beyond this horizon right now, vanishing from view forever, carried away by the unstoppable expansion of space. The idea of a cosmic horizon comes from something deceptively simple. Light has a speed limit. Photons, the messengers of the universe, travel at 26,000 miles per second. Fast enough to circle the Earth 7 times in 1 second, but not infinite. That means the light we see from distant stars and galaxies has taken time to reach us. When you look at the moon, you see it as it was about a second ago. The sun? You're looking 8 minutes into the past. And when you look at the farthest galaxies, you are seeing them as they were billions of years ago, when the universe was young. The farther away you look, the further back in time you see. But this backward view has a limit. The universe is only about 13.8 billion years old, so in theory, we shouldn't see anything older than that. Yet because the universe has been expanding all along, the true limit is even stranger. The farthest galaxies we can detect today are not 13. Space has stretched so much during the journey of that light that our horizon extends far beyond what the age of the cosmos might suggest. This horizon defines the observable universe, the bubble of space we can see from Earth. Anything beyond it lies forever hidden, not because it doesn't exist, but because its light hasn't had enough time to reach us, and never will. The observable universe is vast, containing perhaps 2 trillion galaxies, but it is only a fraction of the whole. Beyond our horizon, the universe may stretch endlessly, perhaps infinitely, but it is inaccessible, as unreachable as the future itself. We are prisoners of light, confined to the part of the cosmos whose photons have had time to arrive. And here's where things get unsettling. The cosmic horizon is not fixed. Because the universe is expanding, more and more galaxies are being carried beyond it every moment. Imagine standing on a shoreline and watching ships sail away, not because they are moving, but because the ocean itself is stretching between you. One by one they slip over the edge, never to be seen again. That's what's happening right now. Galaxies whose light we can see today are crossing the horizon, their future light stretched beyond reach. Someday, perhaps not too far in cosmic terms, they will disappear from our sky altogether. Their final photons will arrive, and then silence. It is happening in this very second, an endless vanishing at the edges of our reality. The most haunting part is what this means for the future of the night sky. Right now, with powerful telescopes, we can glimpse galaxies billions of light years away. We can map the great cosmic web, the filaments of matter that stretch across unimaginable distances. But billions of years from now, future astronomers may not have that luxury. As expansion continues, driven by the mysterious push of dark energy, more galaxies will slip beyond the horizon. Eventually, only our local group, our Milky Way, Andromeda, and a few dwarf companions will remain visible. The rest will be gone, not destroyed, but erased from sight. The universe will appear smaller, emptier, lonelier. Civilizations born in that distant future may never know the truth. They may look into the sky and see only their local galaxies, believing themselves to live in a static, isolated cosmos, just as humanity once did before Hubble's discovery. The evidence of the wider universe will have vanished beyond reach. This is why cosmologists sometimes speak of a cosmic coincidence. We are living at a privileged moment in history, a narrow window when the expansion has been going on long enough to create vast structures, but not so long that they've all disappeared. We can still see the afterglow of the Big Bang, the cosmic microwave background, still detect galaxies billions of light years away, still piece together the story of cosmic history. In the distant past, the view was too opaque. The universe was a glowing plasma. In the distant future, the view will be too empty. The galaxies gone beyond the horizon. Only now, in this fleeting era, does the cosmos reveal itself. But the cosmic horizon isn't just about what we can see. It also defines what we can ever influence. No signal we send, no probe we launch, no light we shine, will ever cross beyond that horizon. The expansion of space carries those regions away too quickly. They are not only unseen, they are unreachable. The horizon is the edge of causality, the line beyond which we can never touch or be touched. In that sense, the universe is divided into infinite islands, each with its own horizon, each forever separate. We are stranded in our own bubble, able to glimpse others for now, but destined for solitude as expansion accelerates. And yet, the horizon is not entirely bleak. It is also what gives us a sense of scale. It tells us the size of our observable universe, the distance light has traveled, the extent of the story we can uncover. It forces us to confront the limits of knowledge, to accept that no matter how advanced our technology becomes, there are boundaries written into physics itself. The horizon is not a failure of imagination. It is a reminder of the grandeur of what we can still see. Every faint galaxy we detect near that edge is a victory against time, a glimpse into a realm that will soon be gone. The cosmic horizon also raises tantalizing possibilities. If we can only see part of the universe, then what lies beyond? Is it more of the same, an endless stretch of galaxies, clusters, and voids? Or could it be something entirely different? Regions with different physical laws, different constants, different realities. Inflation theory suggests that beyond our horizon, space continues, perhaps infinitely, perhaps bubbling with other universes like foam on an ocean. If that's true, then our horizon is not just a boundary of sight. It's a boundary between our universe and an unfathomable greater multiverse. The thought is dizzying, but also humbling. We are not the center of everything, not the special place where the expansion begins. We are just one raisin in the rising bread, one island in the ocean, one bubble in a vast froth of reality. The cosmic horizon doesn't shrink us. It shows us the scale of the mystery. To realize that galaxies are vanishing right now, one by one beyond our reach, is to feel both the fragility and the grandeur of our moment. Every time you look up at the night sky, you are seeing not just stars and galaxies, but the edge of time itself. The cosmic horizon is out there, invisible but real, a line where light stops telling its story. Beyond it, the universe continues, perhaps endlessly, but forever hidden. We live on this side, in this moment, with this view, and as fleeting as it is enough to remind us of the truth. The universe is vast, restless, and not all of it is ours to know. For most of the 20th century, astronomers believed they had a handle on the fate of the universe. After all, if the cosmos began with a bang and has been expanding ever since, then gravity, the invisible glue of matter, must eventually fight back. The galaxies racing apart should slow down under their mutual attraction, like a ball tossed into the air that decelerates before falling back. Some scientists thought the universe might collapse in a big crunch, reversing its expansion. Others argued it would expand forever, but at a decreasing rate, growing colder and lonelier as galaxies coasted apart. It seemed like a simple tug-of-war between momentum and gravity, and the only question was which side would win. But then came the shock, the twist no one saw coming. The expansion of the universe isn't slowing down at all. It's speeding up. Something unknown, invisible, and deeply unsettling is pushing space itself apart faster and faster. That mysterious force is what we call dark energy. The discovery began in the late 1990s when two independent teams of astronomers set out to measure how fast the universe was decelerating. Using powerful telescopes, they observed distant supernovae, massive stars that explode in spectacular bursts of light at the end of their lives. Type Ia supernovae, in particular, are invaluable because they all explode with roughly the same intrinsic brightness, making them standard candles in the dark of space. By comparing how bright they appear to us with how bright we know they truly are, astronomers can calculate their distance. Combine that with redshift, the stretching of light due to expansion, and you can measure the cosmic speedometer. But when the data came in, it didn't fit the script. The supernovae weren't just farther away than expected. They were dimmer, suggesting the universe had expanded more than anyone thought possible. Instead of slowing, the expansion was accelerating. The two teams, one led by Saul Perlmutter and the other by Brian Schmidt and Adam Rees, arrived at the same stunning conclusion: some unknown force was pushing galaxies apart with increasing strength. In 2011, they were awarded the Nobel Prize for what remains one of the most shocking discoveries in the history of science. So what exactly is dark energy? That's the unnerving part. We don't know. The term dark energy is a placeholder, a name for our ignorance. It's the label we give to the fact that the equations of the universe don't balance unless there is some form of energy filling space itself, driving expansion faster and faster. Unlike dark matter, which we infer from its gravitational pull, dark energy doesn't clump, doesn't attract, doesn't behave like any substance we know. Instead, it seems to be woven into the fabric of space, an intrinsic property of emptiness itself. In fact, Albert Einstein may have stumbled upon the idea decades earlier. When he first applied his theory of general relativity to the universe, he realized that gravity alone should make space collapse. To counteract this, he added a term to his equations, the cosmological constant, a kind of anti-gravity force that kept the universe stable. Later, when Hubble discovered the expansion of the universe, Einstein abandoned the constant, calling it his greatest blunder. But the accelerating universe suggests it wasn't a blunder at all. The cosmological constant may have been real all along, a faint energy of the vacuum itself, now rebranded as dark energy. If dark energy is the cosmological constant, it means empty space has a built-in pressure that pushes outward, a property of the vacuum that defies intuition. Quantum theory even suggests that empty space is not truly empty, but seethes with fluctuations, particles popping in and out of existence. Perhaps those fluctuations create the energy we see as acceleration. The problem? The numbers don't match. Quantum theory predicts a vacuum energy vastly larger than what we observe, so large it would rip the universe apart instantly. Instead, we see a faint, delicate push, just enough to matter but not enough to overwhelm. Reconciling these numbers remains one of the greatest unsolved problems in physics. Other theories go further, suggesting dark energy might not be constant at all, but dynamic, an evolving field sometimes called quintessence. Unlike a fixed cosmological constant, quintessence could change over time, waxing and waning, perhaps even reversing its effect in the far future. If that's true, then the fate of the universe is not sealed. The acceleration we see today may only be one chapter in a longer story with twists yet to come. But whether constant or dynamic, dark energy is no small player. Measurements suggest it makes up nearly 70% of the total energy content of the universe. Dark matter adds another 27%. Ordinary matter, the stars, planets, gas, and dust we can see, makes up a mere 5%. That means everything familiar, everything we've ever observed, is only a sliver of reality. The rest is hidden in dark matter and dark energy, with dark energy dominating the cosmic budget. The most powerful force in the universe is one we cannot see, cannot touch, cannot fully explain. The implications are staggering. If dark energy continues to drive expansion forever, The universe will not just coast into emptiness, it will accelerate into oblivion. Galaxies will vanish beyond our horizon, leaving only our local group behind. Stars will burn out, black holes will evaporate, and the cosmos will drift into darkness. In this vision, known as the Big Freeze, the universe becomes a cold, lonely place where even light itself stretches into invisibility. But other possibilities lurk. If dark energy grows stronger over time, it could rip apart galaxies, stars, planets, and even atoms in a catastrophic Big Rip. If it weakens or reverses, the universe could collapse back into a fiery Big Crunch. The truth lies hidden in the nature of dark energy, a mystery we are only beginning to probe, and probing it is no easy task. Unlike dark matter, which can be studied through its gravitational effects on galaxies, dark energy acts everywhere at once, subtle and pervasive. Scientists map it by observing the large-scale structure of the universe, the clustering of galaxies, the bending of light by gravity, and the patterns in the cosmic microwave background. Projects like the Dark Energy Survey and the upcoming Vera Rubin Observatory are dedicated to unraveling its nature. But for now, every clue only deepens the enigma. What makes dark energy so haunting is not just its mystery, but its inevitability. We live in a universe where expansion is not optional. It is accelerating beneath our feet, woven into the vacuum, unstoppable and relentless. We cannot escape it, cannot shield ourselves from it, cannot even see it directly. We can only measure its effect as galaxies slip away, as distances stretch, as the future grows colder. It is a reminder that reality itself has rules beyond our grasp, forces beyond our comprehension, destinies beyond our control. And yet, there is something strangely poetic about it. The very force that ensures the universe will fade into silence also ensures that we are here to witness it. If dark energy was stronger, galaxies might never have formed. If it were weaker, the universe might have collapsed long ago. Somehow, against impossible odds, it is just right. Small enough to allow stars and planets and life to emerge, but strong enough to dominate the cosmic future. In that balance lies the greatest mystery of all. Why does the universe have the properties it does? Is it chance, or design, or the inevitable outcome of countless universes, where only the balanced ones survive? For now, the answer is beyond us. But one truth remains clear. Dark energy is not just a scientific puzzle, it is the defining feature of our cosmic age, the force shaping the destiny of everything. We live in its grip, we breathe in its consequences, and we can never escape its reach. The universe is expanding, faster and faster, and in that acceleration lies both our past and our future. It is the revelation that turned cosmology upside down, the discovery that shattered our assumptions, the mystery that still whispers from the darkness. The universe is not slowing, it is racing, and the finish line is still unknown. When you look up at the night sky, it feels like you're seeing the universe itself laid bare. Stars glitter like diamonds, galaxies stretch like luminous rivers, and the black void between them seems like the true background of reality. But appearances are deceptive. What our eyes reveal is only the thinnest skin of the cosmos, a shimmering veneer covering something far stranger beneath. Because the truth is, most of the universe is invisible. Most of it is hidden. And one of the greatest mysteries in science is that the stars, planets, and galaxies we see are only the tip of the iceberg. Beneath them lies a hidden web of matter that neither glows nor reflects, yet shapes everything we know. That web is called dark matter. The story of dark matter began with an astronomer named Fritz Zwicky in the 1930s. He was studying the Coma Cluster, a swarm of galaxies bound together by gravity. By measuring their speeds, he realized something was terribly wrong. The galaxies were moving too fast. According to the visible matter alone, the stars and gas, they should have flown apart, scattering into space. Yet the cluster held together as though some unseen glue was binding it. Zwicky called this missing mass dunkel materie, or dark matter. At first, few paid attention. It seemed like a wild claim, and Zwicky was known for his eccentric personality. But decades later, the evidence returned with a vengeance. In the 1970s, Vera Rubin and Kent Ford observed the rotation curves of spiral galaxies. If you imagine a galaxy spinning, the stars near the center should orbit faster than those at the edges, just as planets close to the sun move faster than those farther out. But when Rubin measured the speeds, she found something shocking. Stars far from the galactic center were moving just as fast as those near the middle. The outer regions weren't slowing down, they were whipping around at impossible speeds. The only explanation was that an enormous amount of unseen matter was providing extra gravity, holding the galaxies together. The idea of dark matter was no longer fringe. It was unavoidable. Today we know that dark matter makes up about 27% of the universe, while ordinary matter, the stuff of stars, planets and people, is a mere 5%. That means for every atom in your body, there are 5 times more particles of something else, invisible, unknown, shaping the very stage on which life plays out. Without it, galaxies wouldn't form, stars wouldn't cluster, the cosmic web itself wouldn't exist. In a strange sense, dark matter is the true architect of the universe, the scaffolding upon which all visible structures are built. But what is it? That's the haunting part. We still don't know. Dark matter is not made of atoms. It doesn't emit light or absorb radiation. It passes through us silently, unannounced. Billions of dark matter particles may be streaming through your body every second, yet you don't feel a thing. The best theories suggest it could be made of exotic particles, WIMPs, weakly interacting massive particles, axions, or sterile neutrinos. Each has its own strange properties, but none has been confirmed. Decades of experiments, from underground detectors, shielded by mountains, to massive particle colliders, like the LHC, have searched for a direct sign of dark matter, but so far it has remained hidden. And yet, while invisible, its fingerprints are everywhere. Look at the way galaxies cluster across billions of light years, and you see the pull of dark matter shaping the cosmic web. Look at the bending of light from distant galaxies, distorted by gravity in a phenomenon called gravitational lensing, and you see the invisible mass magnifying the view. Look at the cosmic microwave background, the baby picture of the universe, and you see patterns that only make sense if dark matter was present, quietly shepherding matter into clumps that would one day become galaxies. The evidence is overwhelming. Dark matter is there. We just don't know what it is. The most haunting realization is that dark matter doesn't just exist. It dominates. The stars that fill our night sky, the glowing arms of galaxies, the fiery birthplaces of nebulae, all of that is secondary, mere decoration atop an invisible skeleton. If you could see the universe in dark matter, picture would be utterly different. You wouldn't see scattered galaxies like islands in a void. You would see a vast web of filaments, immense structures stretching across billions of light years, connecting galaxy clusters like beads on a string. This cosmic web is the true architecture of the universe, and dark matter is its builder. This hidden web also holds clues to one of the greatest mysteries, how the universe evolved. In the earliest moments, matter was spread nearly evenly, with only tiny fluctuations, but gravity, working through dark matter, amplified those fluctuations. Where there was slightly more dark matter, its pull drew in more gas and dust, eventually forming stars and galaxies. Without dark matter's invisible hand, the cosmos might have remained smooth and featureless forever. That means we owe our very existence to something we cannot see, cannot touch, cannot fully understand. Every star that shines, every planet that orbits, every life that breathes, all of it is a side effect of dark matter quietly pulling strings in the background. And yet, the puzzle grows stranger. If dark matter is so abundant, why can't we catch it? Why has it eluded decades of searches? Some scientists wonder if we're looking in the wrong place. Maybe dark matter isn't WIMPs or axions at all. Maybe it's something even stranger. Primordial black holes formed in the first seconds after the Big Bang, too small to see but numerous enough to account for the missing mass. Or perhaps the problem isn't with matter, but with our theory of gravity itself. Modified Newtonian dynamics, or MOND, suggest gravity behaves differently on large scales, eliminating the need for dark matter entirely. But so far the weight of evidence favors the invisible particles, even if they remain stubbornly hidden. Dark matter is more than a scientific mystery. It's a philosophical one. It reminds us that our senses are deceivers, that the glowing stars we revere are only the surface of a much deeper reality. It humbles us, forcing us to admit that most of the universe is beyond our grasp, and it challenges us, daring us to invent new tools, new ideas, new ways of seeing the unseen. Perhaps one day, a detector buried deep underground will flash with the first unmistakable sign of a dark matter particle colliding with an atom. Or perhaps a new telescope will reveal patterns in the cosmic web that point to its true nature. Until then, we live in a universe haunted by ghosts, bound together by an invisible web, walking through a reality that is mostly hidden. And here's the most chilling thought. Dark matter is not just out there in distant galaxies. It's here, all around us, filling this room, flowing through your body, silently shaping the Milky Way that carries us. We are immersed in it, sustained by it, ignorant of it. The universe is not what it seems. It is darker, stranger, and more mysterious than we ever imagined. There are places in the universe where gravity reigns with such absolute authority that nothing, not light, not time, not even the laws of physics as we understand them, can escape its grasp. These are black holes, the monsters of gravity, cosmic abysses that warp reality itself. They are not objects in the ordinary sense. They are regions where matter has been crushed beyond recognition, where space folds in on itself, and where the future funnels into a single direction inward. To encounter a black hole is to confront the end of everything you thought you knew about space and time. The story of black holes begins with the death of stars. Massive stars live fast and die violently, burning through their fuel until their cores collapse under the weight of their own gravity. If the star is heavy enough, dozens of times the mass of the Sun, this collapse doesn't stop with the formation of a neutron star, an ultra-dense ball where protons and electrons have fused into neutrons. Instead, the collapse continues without limit, compressing matter into a point of infinite density, a singularity. Around that singularity lies the event horizon, the boundary of no return. Cross it, and escape becomes impossible. No rocket could fight back, no signal could get out, no cry could ever be heard. The concept seemed so absurd when it was first imagined that even scientists hesitated to believe it. Einstein himself was skeptical. The mathematics of general relativity predicted that gravity could collapse matter into such extremes, but Einstein thought nature would find a way to prevent it. Yet over the decades the evidence piled up. Strange stars orbiting invisible companions, galaxies with bright jets of energy shooting from their cores, ripples in space-time itself. All of it pointed to the existence of black holes. What began as a mathematical oddity became one of the most terrifying realities in the cosmos. Black holes come in many sizes, from stellar mass black holes a few times heavier than the Sun, to supermassive black holes that weigh millions or even billions of solar masses. At the center of nearly every galaxy lurks one of these giants, including our own Milky Way. The black hole at our core, known as Sagittarius A, is about 4 million times the mass of the Sun. For decades it remained invisible, a hidden tyrant bending the orbits of stars around it. Then in 2019, humanity achieved something once thought impossible. The Event Horizon Telescope captured the first image of a black hole's shadow, a dark circle surrounded by glowing plasma. It wasn't a photograph of the singularity itself that remains forever hidden, but the silhouette it casts against the light around it, the mark of gravity so strong it devours space. To understand why black holes are so terrifying, you need to grasp the nature of their event horizons. From outside, you could orbit a black hole safely at a distance, but inch closer, and the pull grows overwhelming. If you crossed the event horizon, there would be no turning back. To an outside observer, time appears to freeze at the edge, as though you are suspended forever at the brink. But from your perspective, you would plunge inward in a finite time, racing toward the singularity where the laws of physics break. This duality, the frozen view from outside, the doomed plunge from inside, shows just how strange relativity becomes in the shadow of ultimate gravity. The singularity itself is the ultimate mystery. It is not simply a dense ball of matter, but a breakdown of the equations we use to describe reality. Infinity is not a number but a failure of knowledge, a signal that our theories are incomplete. At the singularity, space and time as we know them cease to exist. Whether the universe hides new physics there, a bridge to another dimension, a wormhole, a bounce into another universe, we do not know. Black holes are not just monsters. They are gateways to the unknown, laboratories for the edges of physics. But their influence is not confined to their depths. Black holes shape galaxies themselves. The supermassive ones at galactic centers don't just sit quietly. They feast, devouring stars and gas, and in the process unleash torrents of energy. Matter falling toward a black hole forms an accretion disk, swirling faster and faster, heated to incredible temperatures, until it radiates across the spectrum. In some cases, magnetic fields funnel material into colossal jets that shoot across intergalactic space, stretching for millions of light years. Paradoxically, these monsters that swallow light also illuminate the universe, powering quasars so bright they outshine entire galaxies. Without them, the cosmos would look very different. Even more chilling are the effects black holes have on time. Near their horizons, time itself dilates, slowing compared to the outside world. A clock falling into a black hole would tick slower and slower as seen from afar, stretching seconds into centuries. For the falling observer, everything would feel normal, but the outside universe would accelerate wildly, racing toward the future in a blur. In this way, black holes are not only prisons of space, but distorters of time, warping reality in ways our intuition cannot follow. And then there's Hawking radiation. In the 1970s, physicist Stephen Hawking showed that black holes are not completely black. Quantum effects near the horizon allow them to emit tiny amounts of radiation, slowly leaking energy over unimaginable timescales. This radiation could cause black holes to evaporate, shrinking until they vanish in a final burst. This discovery shook the foundations of physics, because it raised questions about information. If black holes evaporate, what happens to the information about the matter that fell in? Does it vanish forever, violating the sacred principle of quantum mechanics? Or does it escape somehow, encoded in the radiation? This information paradox remains one of the greatest puzzles in science, a conflict between relativity and quantum theory that has not yet been resolved. Black holes also challenge our imagination about the future of the universe. In a cosmos dominated by dark energy, galaxies will drift apart, stars will burn out, and black holes may become the last surviving giants. Over trillions of years, they will consume whatever matter remains, until even they begin to evaporate. The final fireworks of the universe may not come from stars, but from black holes shrinking into nothingness, leaving only a cold, empty void behind. These monsters of gravity may also be the last storytellers of reality. But perhaps the most haunting truth is this: black holes are not distant curiosities. They are part of our own galaxy, part of our cosmic neighborhood. Stellar black holes pepper the Milky Way, unseen companions born from ancient supernovae. The supermassive giant at our center pulls at us even now, its presence steady and invisible. We live in their shadow, whether we realize it or not. And every time we stare into the night sky, we are looking at a universe shaped by their hand. Black holes remind us that the universe is not gentle. It is not safe. It is a place where matter collapses, where time warps, where reality itself falters. They are the monsters of gravity, the abysses at the edge of knowledge, the dark hearts of galaxies. To understand them is to confront the limits of human comprehension. To study them is to look into the face of infinity, and to live in a universe that contains them is to know that the cosmos is far stranger, far darker, and far more terrifying than we ever imagined. Every star in the night sky is a story in progress, a furnace burning through its life cycle on timescales that dwarf human history. They appear eternal to us, fixed in constellations passed down for thousands of years, but they are not everlasting. Stars are living things in the cosmic sense, born, maturing, and eventually dying in ways as violent and spectacular as any event in the universe. To understand the fate of stars is to glimpse the very heartbeat of the cosmos, because it is in their lives and deaths that the elements of planets, oceans, and even our bodies are forged. Stars are both creators and destroyers, alchemists of existence, whose destinies are written in the balance between gravity pulling inward and nuclear fire pushing outward. It all begins in the cold depths of interstellar space, where clouds of gas and dust drift in silence. Left undisturbed, these clouds can float for millions of years. But gravity is patient, and when a region of the cloud becomes dense enough, it begins to collapse, pulling material inward. As the gas falls, it heats, and a newborn star called a protostar forms in the center. When the core temperature rises to about 10 million degrees Celsius, hydrogen atoms begin to fuse into helium, releasing energy. The star ignites, balancing gravity's crush with the outward pressure of fusion. This moment marks its true birth, and it enters what astronomers call the main sequence. For most stars, the main sequence is the long, stable Middle Age, a period where hydrogen fuses steadily in the core. Our Sun is in this stage now, halfway through its 10 billion-year lifespan. The energy released keeps it shining brightly, holding planets in orbit and fueling life on Earth. Massive stars, however, burn through their fuel much faster, living only millions of years, while smaller red dwarfs can sip their hydrogen for trillions, outliving everything else in the galaxy. The fate of a star is determined by its mass, a simple but unforgiving rule. The heavier it is, the faster it lives and the more violent its death. Eventually the fuel runs low. In stars like our Sun, once hydrogen in the core is depleted, fusion slows, gravity pushes inward, and the core contracts. This contraction raises the temperature, igniting hydrogen in surrounding layers. The outer layers swell dramatically, and the star becomes a red giant. Our Sun, 5 billion years from now, will expand so enormously that it may engulf Mercury and Venus, possibly even Earth. The sky will blaze with its swollen form, a fiery monster filling the heavens, but the core will continue shrinking. When temperatures climb high enough, helium fusion begins, fusing helium into carbon and oxygen. For a time, the star stabilizes again, but this reprieve is short-lived. When the helium is gone, the Sun will have no more fuel to burn. Its outer layers will drift away into space, forming a glowing shell of gas called a planetary nebula. What remains at the center is a white dwarf, a dense, Earth-sized ember containing the core's leftover carbon and oxygen. It no longer fuses elements, it simply radiates away its heat, cooling slowly over billions of years. In the distant future, it will fade into a cold, dark remnant, known as a black dwarf. This is the quiet fate of stars like our Sun, not an explosion, but a slow fading into silence. But the fates of massive stars are far more violent. When a star many times larger than the Sun exhausts its hydrogen and helium, the process continues. The core contracts, igniting heavier and heavier elements, carbon into neon, neon into oxygen, oxygen into silicon, silicon into iron. Each stage happens faster than the last, until the star builds an iron core. And here lies the limit, the trap no star can escape. Iron cannot produce energy through fusion. Instead, the fusion process stops, and gravity takes over completely. In a fraction of a second, the core collapses, crushing protons and electrons into neutrons, forming a neutron star. The outer layers rebound off this collapsing core in a catastrophic explosion, a supernova. Supernovae are among the most violent events in the universe. For a brief moment, a single star can outshine an entire galaxy. The blast hurls heavy elements into space: gold, uranium, calcium, iron, seeding the cosmos with the building blocks of planets and life. Every atom of iron in your blood, every bit of calcium in your bones, every trace of gold in jewelry, was forged in the heart of a star and scattered by a supernova billions of years ago. To say we are made of stardust is not poetry, it is literal truth. The collapsed core of a massive star becomes either a neutron star or, if heavy enough, a black hole. Neutron stars are city-sized objects, so dense that a teaspoon of their material would weigh billions of tons. They can spin hundreds of times per second, emitting beams of radiation like cosmic lighthouses called pulsars. Black holes, of course, are the ultimate fate of the most massive stars, collapsing beyond even the neutron star stage, creating singularities hidden behind event horizons. In these remnants, gravity wins absolutely. But not all stars live dramatic lives. The most common stars in the universe are red dwarfs, small and faint, but incredibly long-lived. While massive stars die in a few million years, red dwarfs can burn for trillions. None have yet reached the end of their lives, because the universe itself is not old enough. Their eventual deaths will be quiet, their fuel used so efficiently that they fade into white dwarfs without ever becoming red giants. In the far future, long after brighter stars like the Sun are gone, red dwarfs will still glow faintly, the last torches in an aging universe. The ultimate fate of all stars ties directly into the fate of the universe itself. If expansion continues as it does today, stars will form for billions more years, but eventually the raw gas will run out. Galaxies will grow quiet, no new stars igniting, only the embers of old ones cooling in the dark. The cosmos will enter the so-called degenerate era, dominated by white dwarfs, neutron stars, and black holes. Over trillions and quadrillions of years, even those will fade, leaving only black holes and cold remnants in an ever-expanding void. The lives and deaths of stars are not just about light, they are about transformation. Stars take the simplest element, hydrogen, and through nuclear fire create complexity: helium, carbon, oxygen, iron. Without their cycles of birth and death, the universe would be barren. Every planet, every ocean, every living thing is a byproduct of stellar evolution. Stars are cosmic engines, and their fates are written into everything we are. When you look at the stars tonight, you are not just seeing pinpricks of light. You are seeing life cycles frozen in different stages. Some are newborns, still wrapped in nebulae. Others are middle-aged, burning steadily. Some are already doomed, fated to swell, explode, or collapse. And some may already be gone, their light still traveling across space, arriving long after their deaths. The night sky is not timeless. It is a graveyard and a nursery, a living tapestry of creation and destruction. The fate of stars is, in the end, our fate too. Without them, there would be no planets, no oceans, no people. Their deaths gave us the raw materials of life. Their futures will shape the final story of the cosmos. To understand them is to understand ourselves, and to accept that nothing lasts forever, not even the stars that light our skies. They burn, they fade, they die, and in their death, they give us everything. If stars are the atoms of the universe, then galaxies are its molecules, grand structures that bind them together, organize them into vast cities of light scattered across the cosmic web. To gaze at a galaxy is to see billions, sometimes trillions, of stars moving in unison, swirling in spirals, clustering in ellipses, or forming irregular, chaotic shapes. From the Milky Way that holds our sun to the colossal clusters at the edge of our view, galaxies are the true building blocks of the cosmos. And yet, like everything else in the universe, they are not eternal. They live, they evolve, they collide, and they die. Their story is our story, because without galaxies there would be no stars, no planets, and no life. The Milky Way itself is a spiral galaxy, a grand disk of stars stretching about 100,000 light-years across, its spiral arms curling like whirlpools of starlight. In its core lies a dense bulge of older stars, and at the very heart, a supermassive black hole, Sagittarius A, around which everything else dances. Our sun sits in one of the spiral arms far enough from the center to enjoy relative calm, orbiting the galactic core once every 2. That means since Earth formed, our planet has circled the galaxy more than 20 times, a reminder of how deeply we are bound to this colossal structure. And yet the Milky Way is just one among trillions. When the Hubble Space Telescope pointed at what looked like empty darkness in the 1990s, it revealed thousands of galaxies in a single patch no larger than a grain of sand held at arm's length. Every point of light was not a star, but an entire galaxy, each with its own history, its own black holes, its own planets, its own possibility. Galaxies come in many forms. Spirals, like our Milky Way or Andromeda, are the most picturesque, with their graceful arms winding outward. Elliptical galaxies are massive, football-shaped giants, often containing older stars and less gas, quiet graveyards where little new star formation occurs. Irregular galaxies are chaotic, distorted shapes, often the result of collisions or gravitational interactions. But no matter their form, all galaxies share the same essence. They are bound communities of stars, gas, dust, and dark matter, existing as islands in the ocean of the universe. Dark matter, in fact, is the hidden scaffolding that makes galaxies possible. The visible stars and gas alone are not enough to hold them together. The way stars orbit in galaxies reveals an invisible halo of mass extending far beyond the visible edges, a cloak of dark matter that outweighs the luminous contents. Without it, galaxies would fly apart. This means that every galaxy is not just a city of stars, it is also a ghostly shadow of something unseen bound together by a force we cannot yet explain. Galaxies are not solitary either. They gather into groups and clusters, pulled together by their mutual gravity. Our Milky Way belongs to the local group, a collection of more than 50 galaxies dominated by two giants, the Milky Way and Andromeda. Beyond that lies the Virgo cluster, a much larger assembly, and beyond that, the great filaments of the cosmic web, stretching for billions of light-years. On these scales, galaxies are not static. They are social, interacting, colliding, and merging in dances that last hundreds of millions of years. The destiny of the Milky Way is already written in this cosmic choreography. In about 4 billion years, it will collide with Andromeda, a spiral galaxy slightly larger than ours. At first, the galaxies will pass through each other, their stars rarely colliding directly because the spaces between them are so vast. But gravity will warp their shapes, drawing out long tidal tails of stars and gas. Over time, the galaxies will merge into a single larger elliptical galaxy, sometimes called Milky Way. For the stars inside, the night sky will blaze with new patterns as galaxies blend, creating cosmic fireworks of star formation triggered by the clash of gas clouds. Humanity may not be around to witness it, but the universe itself will continue its dance, indifferent to the fates of its inhabitants. The lives of galaxies are tied to their ability to form stars. Young galaxies rich in gas are vibrant, glowing with nebulae where new stars are born, but over billions of years, they exhaust their supply in elliptical galaxies where star formation has largely ceased. The glow comes mostly from ancient red stars. These galaxies are the retirement homes of the cosmos. Fading slowly as their stellar populations age, spirals like the Milky Way are still active, with nurseries of stars forming in their arms. Irregular galaxies often flare with bursts of star formation triggered by gravitational encounters. A galaxy's fate depends on its mass, its environment, and its history of collisions, but all follow the same general arc: birth, growth. Some galaxies are anything but quiet. At their centers, supermassive black holes can erupt in fury when fed by inflowing gas, creating what astronomers call active galactic nuclei. These can shine brighter than the galaxy itself, releasing jets of particles that travel across millions of light years. Quasars, the most luminous of these, are among the brightest objects in the universe, powered by black holes devouring matter at ferocious rates. For distant observers, these cosmic lighthouses are beacons from the early universe, revealing galaxies as they were billions of years ago. The paradox of galaxies is that their darkest hearts, black holes that swallow everything, can also produce the brightest displays we know. Galaxies are also storytellers of cosmic history. By studying their shapes, colors, and motions, astronomers can reconstruct how the universe evolved. Young galaxies in the early universe were often small and irregular, gradually merging into the larger, more organized forms we see today. Their light, stretched by billions of years of expansion, carries with it the story of how matter assembled, how dark energy accelerated expansion, and how the cosmic web emerged. Each galaxy is not just a city of stars, it is a fossil, a record of the universe's past. And yet, for all their grandeur, galaxies are fragile against the relentless march of cosmic time. In a universe ruled by dark energy, galaxies outside our local group are destined to slip beyond our cosmic horizon. Their light will no longer reach us, and the universe will seem emptier with each passing billion years. The cosmic cityscape we see today will not last forever. Only our local group will remain, drifting in a sea of dark. The grand clusters and filaments will fade, leaving isolated galactic remnants as the last visible traces of structure. But in this moment, galaxies give us something extraordinary. They remind us that the universe is alive with structure and beauty, that the night sky is not random but the product of vast, interconnected systems. To look at a galaxy through a telescope is to look across time, to witness billions of stars woven into a single pattern, to see creation itself playing out on scales almost too vast to comprehend. Each galaxy is a city, but also a story, a chapter in the larger book of the cosmos. The fate of galaxies mirrors the fate of the universe. They grow, they merge, they exhaust themselves, they fade. And yet in their cycles, they create everything we know. Without galaxies, stars would be scattered, never clustering, never forming planets. Without galaxies, there would be no place for life. They are the cradles of existence, the engines of cosmic evolution, the scaffolding of reality. And even as they vanish beyond horizons, even as they collide and die, they leave behind the light that tells their story. Tonight, when you look at the faint smudge of Andromeda in the sky, remember that you are looking at another city of stars, a neighbor on a collision course, a galaxy filled with billions of suns and perhaps trillions of worlds. It is the nearest chapter in a story that spans the universe, a story written not in words but in light. Galaxies are the universe's handwriting, and every star within them is a letter. Together they form a script too vast to ever read in full, but clear enough to remind us that we are not alone. We live not just in a galaxy but in a cosmos filled with them, cities of stars scattered across eternity. When you step back far enough, the universe reveals itself in a way that is almost impossible to imagine. Individual stars disappear into galaxies, galaxies blur into clusters, and clusters stretch into something even greater, a colossal tapestry known as the cosmic web. This is the large-scale structure of the universe, the grand architecture that binds everything together. It is not random, not chaotic, but patterned, shaped by gravity and dark matter into a structure that resembles a living network, like neurons firing in a brain or filaments in a spider's web. To study it is to glimpse the skeleton of the cosmos itself, the invisible framework upon which all of existence hangs. The first hints of this structure came when astronomers began charting the positions of galaxies on a large scale. At first, they expected a smooth distribution, galaxies sprinkled evenly like stars in the night sky. But the maps told a different story. Instead of being spread uniformly, galaxies were found to cluster into long chains, walls, and filaments, separated by enormous voids, regions of near emptiness spanning hundreds of millions of light-years. It was as if the universe had woven itself into a vast cosmic net, with matter gathered along the threads and emptiness filling the spaces between. One of the most famous discoveries of this kind is the Sloan Great Wall, an immense structure stretching over 1 billion light-years across. Imagine that, a formation so vast that if light started at one end, it would take over 1 billion years to reach the other. And yet even the Great Wall is just one filament among countless others, part of a web that extends across the entire observable universe. These filaments connect clusters of galaxies into superclusters, forming the backbone of the cosmos. In between lie vast voids, regions where matter is sparse, as though the universe itself had hollowed out cavities in its fabric. The driving force behind this structure is gravity, working hand in hand with dark matter. In the earliest moments after the Big Bang, matter was almost evenly spread, with tiny fluctuations in density, but those small differences were amplified over billions of years. Where there was slightly more matter, gravity pulled in more, forming knots and filaments. Dark matter, invisible yet abundant, provided the scaffolding, the unseen framework upon which galaxies could form. Without dark matter, the universe would never have organized itself into this web. It would have remained smooth, bland, and lifeless. Instead, the cosmic web emerged, shaping the universe into a vast network of connections. To visualize it, imagine pouring cream into coffee and watching the tendrils stretch and twist, leaving behind filaments and empty spaces. Or imagine neurons branching in a brain, each connected by thin lines of tissue. The cosmic web looks eerily similar, as if the universe itself were a living organism. In fact, some scientists have even compared the distribution of galaxies to the structure of the human brain, noting that both follow similar patterns of nodes and filaments. The universe, it seems, thinks in webs. The voids are just as important as the filaments. These immense regions, sometimes hundreds of millions of light-years across, are nearly empty, containing only a few stray galaxies. They act like cosmic bubbles, pushing matter toward the walls and filaments around them. If you could somehow stand inside a void and look outward, the universe would appear clustered around the edges, distant galaxies forming a faint, glowing shell around an ocean of darkness. In a sense, the universe is more empty than full, and the cosmic web is a delicate lace of matter suspended across this vast nothingness. The discovery of the cosmic web changed how we think about the universe. No longer is it a random scattering of galaxies. It is a system, a structure, a design emerging naturally from the laws of physics. It shows that the universe has order on the grandest scales, patterns written into its very fabric. And it also raises haunting questions. If this web is shaped by gravity and dark matter, then what role does dark energy play? Because while matter pulls together, dark energy pushes apart, accelerating the expansion of the universe. Over billions of years, dark energy will stretch the web thinner and thinner, pulling its filaments apart until galaxies beyond our local groups slip beyond the cosmic horizon. The web, magnificent as it is, will not last forever. But for now, it is the stage upon which cosmic history unfolds. Galaxies form along its filaments, drawn together into clusters where the threads intersect. Collisions and mergers occur most often at these nodes, fueling starbursts and feeding black holes. The web is not static. It is alive, constantly evolving, matter streaming along filaments like rivers toward the densest regions. Even now, the Milky Way and Andromeda are part of this flow, drifting along filaments toward the Virgo cluster, our local supercluster. We are passengers on the currents of the cosmic web, carried by forces we cannot feel but that shape everything we know. The sheer scale of this structure defies comprehension. The observable universe spans about 93 billion light-years, and within it the cosmic web stretches like a vast network of veins and arteries. Each filament contains billions of galaxies, each galaxy containing billions of stars, each star possibly orbited by worlds. It is a fractal of existence, layers upon layers of structure, all tied together by gravity. To realize this is to feel both insignificant and connected, a tiny spark inside a network that spans the cosmos. What makes the cosmic web even more mysterious is that we can't see it directly. The filaments themselves are composed mostly of dark matter and thin gas, too diffuse to glow in visible light. Astronomers detect it through indirect means, the way galaxies cluster, the way light bends through gravitational lensing, the faint signatures of hydrogen gas, lit by distant quasars. Piece by piece, the map of the web emerges, a ghostly lattice slowly revealed. We see only the brightest lights strung along its threads, but we know the true skeleton is much larger, hidden beneath. In many ways, the cosmic web is the universe's greatest paradox. It is immensely large, spanning billions of light-years, yet its basic shape was determined in the tiniest moments after the Big Bang, seeded by quantum fluctuations. Tiny ripples in the early universe grew into walls and filaments that now span unimaginable distances. It means that the grandest structures are linked to the smallest events, that the web of galaxies is ultimately tied to quantum jitters in the first fractions of a second. The large-scale structure of the universe is not just vast, it is deeply connected, a chain linking the microscopic to the cosmic. And as breathtaking as the web is, it is only temporary. Billions of years from now, dark energy will stretch space so quickly that distant filaments will vanish beyond reach. The cosmic web we map today will dissolve into isolated islands of galaxies, separated by gulfs of darkness. The story of the universe is not just creation, but dispersal. The web, vibrant and intricate, is a fleeting stage in a larger play. Future civilizations, if they exist, may never know the universe was once filled with countless galaxies. They will see only their local cluster, the rest gone forever. But for us, now, we can still see it. We can map it. We can wonder at its scale and beauty. The cosmic web is the ultimate reminder that the universe is not empty, not chaotic, but alive with patterns on scales beyond imagination. It is the universe's hidden architecture, its scaffolding, its skeleton. It is what holds galaxies in place, what gives shape to everything we see, what carries us silently through the dark. When you look at the night sky, you are not just looking at stars, you are looking at nodes on an invisible web, filaments stretching across eternity, a network so vast that we can barely grasp it. The cosmic web is not just out there, it is the universe itself, the grand design written in threads of matter and shadow. And to know it exists is to realize that we are not just floating in darkness. We are woven into a fabric far larger than ourselves, part of a cosmic tapestry that binds us to the stars, to the galaxies, and to the infinite web of creation. When we first looked to the skies, we thought we saw eternity, unchanging stars, silent emptiness, a universe that simply was. But now we know better. The universe is not still. It is not simple. It is alive, restless, and layered with mysteries that cut deeper the more we uncover them. Space is not empty. It bends, ripples, and hums with hidden energy. Galaxies are not static. They collide, merge, and dissolve into something new. Stars are not eternal. They are born. They burn and they die in flames that forge the very atoms of our bodies. Everywhere we look, the cosmos tells a story of change, of cycles, of beginnings and endings that stretch far beyond our lifespans. And yet, in all of this vastness, one truth lingers. We are part of it. Every atom in our bodies was forged in the heart of a star, scattered across the galaxy by an ancient supernova, gathered again into a planet orbiting a yellow sun. The light in our sky is borrowed from galaxies stitched into a cosmic web, threads of gravity that bind everything together. We are not separate from the universe. We are its expression, its echo, its way of looking back on itself and asking what it all means. But with this knowledge comes humility. For all our telescopes, theories and maps, we still stand at the edge of mystery. Dark matter surrounds us. yet we cannot touch it. Dark energy drives the expansion of the universe, yet we do not understand it. Black holes swallow light, bending reality, hiding their secrets behind horizons we cannot cross. The cosmic web stretches across billions of light years, but we have only glimpsed fragments of its full shape. The universe offers clues, but it guards its deepest truths with silence. Every discovery answers one question and raises 10 more. Perhaps that is the true lesson of the cosmos. Not that it is infinite, but that our curiosity must be. To look at the stars is to accept that we will never see the full picture, never reach the final page of the story. But that is not a defeat. It is an invitation. The mystery is what keeps us searching, what drives us to build better telescopes, to imagine bold theories, to reach beyond the fragile skin of our world and step into the ocean of space. The universe does not owe us clarity, but it gives us wonder, and maybe wonder is more powerful than certainty. Wonder is what made ancient humans trace constellations in the night sky. Wonder is what drove Galileo to point a telescope upward, what inspired Einstein to rewrite the laws of reality, what sent probes across the void to touch other worlds. Wonder is what makes you watch, listen and imagine what lies beyond the darkness. In the end, the universe may fade, stars will die, galaxies will drift apart, even black holes will evaporate into whispers of radiation. The cosmic web will unravel, and silence will return, but here now, we are alive in its most vibrant chapter. We stand at the dawn of knowledge, in a universe still burning, still growing, still singing with light. And though our lives are brief, we have the rare gift of seeing it, of knowing it, of being conscious in a cosmos that spends most of its time asleep. So when you look up tonight, do not see emptiness, do not see distance. See a story still unfolding, a mystery still unsolved, a universe still alive. Because the greatest secret of the cosmos is not that it will end, it's that right now, it is ours to witness.